Okay, thank you, Marvin and Martin. I will now start the lecture. If not mistaken, you should be able to see the title of the title slide now. So the introduction to the ontologies will focus on the use of ontologies to support fair research output. The whole idea of our safety assessment is to assess the safety, and existing data is often an important part of that, and our semantic web approaches are meant to support that. Now, the ontology is one of that. It actually goes back to 2013 or something, 14 maybe, when the nanosafety cluster actually identified the need for a common language. So that was actually literally the nanosafety cluster. And I know that at least Isolde Lynch was involved in the discussions that led to a call for projects to develop a common language. The InanoMapper project or the InanoMapper community proposed that project, and that led to the development of the ontology, but to service the nanosafety cluster. So semantic web technologies were there, which we'll see a bit later during this presentation. But the use was a bit different than what we're proposing in this workshop right now. So today and yesterday, we're really looking at data in a semantic form from the ground up. But we will see in this presentation that while ontologies have use in the semantic web, a very important one, the scope of ontologies actually goes beyond things in the RDF format. And this actually is important because an important thing to realize is that the data that we saw yesterday in or rather verbose representation in these Sparkle endpoints is there for a reason. It doesn't necessarily have to be the endpoint. Can simplify data, which is what you're doing with Sparkle queries, for example. But what is essential to the semantic web is the added information that you did not explicitly have in the data before. And this is obviously also the reason why we're doing ontologies, because each term in an ontology, as we will see, is actually basically just a unique identifier to a concept, and that concept has a description, it has a context, we'll see a number of examples there. These things are not really new either. Ontologies is something that we do in science for a very long time already, and basically just something like the number 0 is actually already something from an ontology. It is a concept by which we represent something from reality. So that is roughly what an ontology does, nothing more, nothing less. Things like the web ontology language and the InanoMapper ontology, they just formalize all this a bit more so that we can more easily reuse these things. So the InanoMapper ontology that was set out to provide a common solution to this community, and so this community is growing, and these are a number of projects. It's not even an exhausting list that are working on and have contributed to this common solution, this common ontology that we have been developing. And so we see the NanoCommons InanoMapper. I already actually immediately see some project labels missing, like the NanoSolvit and Riscon projects. But there are several other projects that Maastricht has not even been involved in that have been using ontologies one way or another, for example, via other past InanoMapper partners. And in some cases, it might be data that results from one of these projects that are now available in a way with ontological annotation. Now, two references for the Inanimate ontology are these two. These come from the Inanimate project at the time. The left one, that is really about the ontology, and the right one is about the Inanimate database. And so the database was a reference implementation based on earlier work in the OpenTox and ToxBank projects, where an open programming interface was being developed. And the OpenTox project actually very early on, so this actually goes back to at least 2011, adopted semantic web technologies, RDF, as part of their database platform. But mind you, the RDF representation in the database, in the OpenTox database, was not actually an intrinsic part of the database. There was no triple store behind it. It was just a basic, sorry, a basic relational database behind it. But the RDF, the translation of that relational database into a semantic format, did allow a lot of things. And actually, I got in contact with the OpenTox project because I was actually using the APIs that they provided and the RDF format to interact with that. And I integrated that at the time with a tool called BioClips. But where I could really benefit from the additional explicit semantics. Now, the Inanimate database actually is being used in a number of current running projects in the Nano Safety cluster, and all these projects, they basically inherit the annotation with ontology terms and this semantic representation. But yeah, more about that later. Now, so the current Inanimate ontology, so the Inanimate project is over, but the project, the ontology itself is being continuously developed by other projects. So NanoCommons had taken over the maintenance of the ontology, and at this moment, the NanoSolvit project is taking over from NanoCommons, because NanoCommons is also ending next year, and NanoSolvit will run until later there. And what we see here is one of the releases made by Laurent. So Laurent was a PhD candidate in our group, and he maintained. He was the maintainer of the database and the release manager of the database. But what you can also see here actually is that is the collaborations that we have had via the Nano Safety cluster, the Workgroup F in particular, with other projects on making sure that the ontology actually follows the current research. Now, the ontology itself actually is represented in the web ontology language, OWL. So if you just want to look at the ontology with an ontology tool like Protege, the link here on this slide is, and I'm wondering, copy link address. I can probably just put the link in the chat here. So that would be the link by which you can open it in Protege. This is also the link that BioPortal and the ontology lookup service and AberOwl look to load the Inanimate ontology and visualize it where needed, allowing you to browse the ontology, as we will see later with BioPortal. So this is a screenshot of BioPortal actually. So you will see that later in the practical session. Now, I already said a bit about what an ontology is, and I will dive a bit more into detail here. So the structure of the Inanimate ontology looks a bit like what we have on the screen here. So what you can see here, I'm not sure if you can see my mouse, but you see the labels like at the top, BFO for basic formal ontology. On the left, the NPO, the nanoparticle ontology, the ENM, that's the Inanimate ontology itself, ENVO, that's an environmental chemistry ontology. There is CHEBI, the ontology of chemical interests, or chemical entities or biological interest. Bit in the middle, the bioassay ontology, and a number more. So these are all ontologies from which the Inanimate ontology reuses bits. And that reuse is really important. And there was an so if you read the NanoMapper paper by Jenna Hastings, you can see the details of why we made that choice. But one aspect of that was really very practical, and one was more theoretical, or well, not theoretical, more fundamental. So the practical thing was that the nanosafety field is really broad, and making ontologies is really expensive. So wherever we could reuse existing content, that would be nice. The more fundamental problem is that a small project like NanoMapper, the project was not that large, cannot take up an effort of this size. If you look at the development of ontologies, you actually see how expensive it is, and it should be domain experts that describe what biology, what chemistry, what toxicology they have been looking at. And of course, a central team can try to get that information, but that's not very efficient. So the NanoMapper project, we developed a platform here where we could reuse parts of these ontologies and integrate that into our ontology, harmonized by all, making it subclasses using the structure of the basic formal ontology. So that gives us a reference framework. Something that I might say something about, because an example of why this is important, for example, is that you have multiple ontological terms for the zeta potential. I will not explain that right now, but if you're interested, we can discuss that later. And using all this, the other really important part, as set aside the reasons why we structured it like this, is basically the arrows that we have here. So very important aspect of ontologies is that things have a hierarchy. So you can see here that everything is basically a basic formal ontology entity. And within that, we have different types of entities. We have dispositions, we have material entities. But an example of a material entity, for example, is a chemical substance. And an example of a chemical substance is, for example, a nanomaterial. Another example is a mixture. So this hierarchy actually is quite relevant. So we can have, for example, specific titanium dioxides, and we can have a class of compounds of titanium dioxides. So the general concept of a titanium dioxide-based nanomaterial. And the same for bioassay. So we can have the general concept of a genotoxicity bioassay, but we can also have a specific genotoxicity bioassay where a particular method is used. And that allows us to do interesting things. So instead of having to enumerate or having to know all the titanium dioxides in a database, we can just basically simply ask for, give me all titanium dioxides, and have the ontological annotation and the hierarchy of the ontology take care of the rest. So this hierarchy, that is why Protégé and Bioportal is interesting, because there you can see the hierarchy, and here we have part of that hierarchy, and we see at the top the BFO entity term, and the disposition, information content entity, material entity, and some further down molecular entity where we have graphene oxides, for example, and we have specific nanoparticles, so different from a nanomaterial, which well, typically is a mixture of individual nanoparticles, where we have nanoparticle in there, and on the nanoparticle we have a lot of different specific nanoparticles. That part is for the materials, but each of these ontologies from which we derive information, like the chemical information ontology ChemInf, have these kinds of theoretical descriptions of the knowledge in that domain. So for chemical information, the ChemInf ontology makes a difference on the left side there between software libraries, the algorithms that are implemented by those libraries, and the algorithms to calculate descriptors. And descriptors there are a bit of information about something else. That's something else, might be a substance descriptor, or it might be a molecular descriptor. And molecular descriptor might be the number of atoms in the molecule, and the substance descriptor might be the melting point of the substance. Now, typically, so the melting point actually is interesting because typically we associate the melting point with the chemical graph descriptor of a molecule. We describe, we annotate, for example, aspirin with its melting point. But the melting point actually is really a property of the substance based on that molecule. So the difference between a single molecule and a collection of molecules. So a lot of ontological details that goes into these things. And when you think about the reuse of all this information, sometimes some of this detail is not relevant, and sometimes it is. And the reason why we think this ontological annotation is important and having that described in a lot of detail is that if we describe our knowledge, our data in enough detail without making the simplifications too early, we give ourselves the freedom to make those distinctions later on. And that is really important. So when you reuse data, when you reuse knowledge and you start seeing differences, well, it might be that the data is wrong. It might also be that your representation is wrong. But you can only figure that out if you can actually see what the original data was. Removing detail is always easier than the other way around. Removing detail you can do by means of a Sparkle query, to give one example out of many. Adding adding detail that's not there is nearly impossible because you don't know what that detail was. That's the upside. The downside, of course, is that your representation is much more detailed, so it takes up more volume, and it takes more time to think about what the data really should look like. So there's a trade-off there. So for the nanoparticle, we have this hierarchy as well, and so here we are looking at a nanoparticle. The nanoparticle has different parts like the coating, the core, and possibly shells. The nanoparticle also has a surface, and the surface has qualities, and the nanoparticle itself has qualities. So Nathan Baker and his team at the time, they made an ontological model of how we can represent nanomaterials. And not shown on this slide is the nanomaterial itself, which consists of one or more nanoparticles. So I made a comment earlier that ontologies can be used in a lot of different things. So we saw a semantic web as one utility, but it's definitely not limited to that. So one example where you can use ontologies actually is just in spreadsheets. So in the end, basically a spreadsheet is just a representation of information as well. But there is one important difference. So there is implicit information here rather than explicit information. So, for example, the explicit information missing here is that the information in cell B2, the 20.3 there, which is a number, actually represents a quality, the size, and has a unit. It is given in cell B1. Now we can see that from this table-like structure that the 20.3 probably refers to the size of that cerium oxide in A2, and the 20.3 is in nanometers, which we can see at the top. And computer has much more problems with that, but it's not just computers, humans also. If you work with real life spreadsheets created by nanosafety domain experts, there is always at least one cell where it's unclear what the people that filled out that spreadsheet actually meant to say. And sometimes that's because of a typo. Sometimes it's just because the explicit information is missing, and you have to guess what the assumption is. You have to guess what the meaning is. Here, for example, we see self-viability in column F. Sorry. It's probably reasonably to assume that these numbers are a percentage, but the information actually is missing from the header. It's probably in column G reasonable to assume that these are DOIs of the articles. They start with 10 period. So that's a good clue. But the information is not explicit. So this implicit information that we have here might be there. But we have to guess, and what you see that is that over time, making these assumptions or restoring those assumptions, if you like, becomes more difficult. People change their terminology. Research terms are not static. So the semantic web solves this by making everything explicit at the expense of being more verbose. So yeah, a lot of articles actually share information in spreadsheets, and this is one of them. It might actually be the source of the previous spreadsheet from the previous slide. Besides the explicit information, there are other things. So I hope you have seen this article from the past. Excel is software. It's not just a representation, but there is software around it, and the software actually makes assumptions itself. So if it looks like a date, it probably is a date, because 90% of the people using Excel is interested in dates and not in genes. So that causes an automatic conversion of gene names into dates. That problem is actually, so this article is from 2004. They more recently redid this calculation, and this still is a huge problem. It's actually such a huge problem that 2 years ago, the Human Genome Nomenclature organization, they actually renamed a couple of gene names so that they don't get converted into dates, just to address this problem. But that means that a lot of databases have to be updated because the old gene names, they're no longer the valid gene names, which is a major interoperability issue. Something, by the way, that we solve in one of our projects in our group in BridgeDB, where we have a project to discover such outdated identifiers. Interestingly, you actually ran into this problem of outdated identifiers yesterday. At least there was some discussion about it, about two databases, Wikidata and another database, the Sparkle query not returning something, which could be figured out in the end by identifiers having slightly different representation. So I'm not sure if I have it on the slide, but Nina Yeliaskova and her team, they actually recently, last year I think, published an article, maybe early this year, very recently anyway, published an article, Your Spreadsheet Can Be Fair, and I may have it on my next slide. I'm not entirely sure. But this is an important thing. So in the NanoMapper project, this is exactly what they did. So they actually developed a platform, NM Data Parser, where they used a configuration file written in the JavaScript object notation to make some of these assumptions that we had explicit, but in a different way. So unlike with the semantic web technology, it's still a spreadsheet and a JSON file here, but adding the missing semantics in the spreadsheet. And the arrows that you can see here links some of that content of the JavaScript object notation to the content in the spreadsheet. The JSON is deliberately a bit hard to read because in reality it's still hard to read. I've been creating these JSON configuration files on 2 occasions, and it actually takes a bit of effort to write down what is in which cell. But the importance of this, the impact of this actually is pretty high, because a lot of projects, they actually work with these kinds of spreadsheets. The input of the data works via these templates, like the JRC templates or the IOM templates. There is a third set of templates actually being used in an unsafety cluster. But for these templates, these kind of JSON configurations are existing, and because they're templates, they have a fixed format. These implicit annotations can be converted into this configuration, allowing a lot of data to be imported into the eNanoMapper-based databases that we have in the cluster. Yeah, so this is zooming in a bit on that JSON file, but what you can see here is a couple of things, and the thing that I want to mention here is not so much the structure, but you can see the reference to positions in the spreadsheet, like the sheet index and the column and row indexes, and in this bit of JSON snippet here, you can also see the ontology annotation. So we see a cell line ontology reference and an experimental vector ontology reference here, which formalizes this idea that we can make parts of the spreadsheet annotated with ontology terms. Okay, yeah. So this was the paper I mentioned earlier. So this was output from the NanoRec and Nanoinformatics projects, but look up this article. It's an interesting read. Your spreadsheets can be fair. So a couple of other ontology use cases, and we didn't do that yet, but the practical session, we're going to look into this a bit. But as I said at the start of this presentation, the NanoMapper ontology and the NanoMapper database, they were tightly linked together. And if you go to search.database.nanoMapper.net, that should still work actually. Let me just check that. There have been some updates to the web services, to the interface. So the screenshot that you see in the back there, that's not what it looks like right now. Right now, you get a landing page with all the different databases that projects that use the NanoMapper database as a data platform. 3 of them are publicly available, like the original eNanoMapper demo that we generated, but also the NanoRec and the NanoRec 2 databases. They have their open licenses given just below the project logo, and for the other project, you see a small lock below the logo, and that is because those projects have not released their data yet. And I'm just looking at the Gracious lock there, actually, because that project is over. And as far as I understood, that data should actually already be free, be open. But so that screenshot on the slide, I'll just copy paste that link actually to this website here as well. So that search interface there that you can see there, you reach these kind of interfaces by clicking the logo of the project, which you can do for eNanoMapper, NanoRec, and NanoRec 2. And if you do that, you get a faceted search interface. Well, you actually have to click search on the next page as well, but you get a faceted search page like the one shown on the slide here. And so, for example, actually for the eNanoMapper project, I'll copy paste that link in the slide. So you can go directly there. It looks a bit nicer, but on the left side, you see a lot of different things. So there are projects where data comes from, there are study providers, and there are, for example, nanomaterial types. And this is taking advantage of this hierarchy that I mentioned that we have from these ontologies. And in fact, if you hover over any of the boxes of the buttons that you have in that left faceted search, yeah, I'm not sure what you're seeing right now. Well, actually, what I might be able to do. Let's just show that for a second. Come on, full screen. So this is the link that I post it in the chat right now. So this is the various facets that this faceted searching has. And if I hover over this, so like here, chemical substance, the pop-up, what is it? The pop-up box that we have here in black says Cabby _59999. That is the ontology identifier for this concept. And for copper, for example, we have an ontology term from the InNanoMapper database. For polymer, it comes from Cabby. Multi-walled carbon nanotube also comes from Cabby. Graphene oxide comes from Cabby. One last one. Well, tungsten also from Cabby in this case. So we can select that, and then we actually just return the materials that are of this type. And they may or may not be directly annotated with the Cabby term 131897, but it can also be one of the subclasses, like exactly what happens if I search for chemical substance. Then I don't get just those things that are specifically annotated with chemical substance, but also all with any of the subclasses of chemical substance. So a use case of the hierarchy of ontologies. Okay. So this is using ontology terms to annotate data, and we can do that at very many levels. Another place where we can do this is annotate research output directly with this. So if we don't want to annotate each compound in a database, in a data set, but rather do this more like a keyword annotation for, as we do for research articles, we can just say, okay, this data set is about this kind of material. And there are solutions for that as well. So we've been working with an Elixir project called Bioschemas that allows us to annotate data sets in multiple ways. And by using bioschemas here, which is using semantic web technologies, search engines like Microsoft Bing, Google, and the smaller ones, they can much more easily extract information from the data set to see what that web page actually says. In this case, provide information about data sets, which makes it a lot easier to find them. So when we start annotating these data sets with keywords, then the search engines will be able to use that. This is very much in and under development, but it's you can see where this is going. If search engines are starting to pay attention to semantic web technologies, that means that they can bring in the computational power actually that allows us to search the full internet, and we're much less reliant on specific providers like a specific publisher or a specific database. So this actually is a bit detail about that bioschemas data set profile. You can see the link there. You can go to bioschemas.org and see the information there. In the NanoCommons project, actually, we also, I'm not sure if I have a slide about that now. We actually created a bioschemas profile for chemical substance as well, with specifically the idea in mind that we can in a fair way describe individual nanomaterials. And a couple of months ago, this was adopted by schema.org. There is no search engine, World Wide Web search engine for chemical substances yet, but this is something being worked on. So we can expect that in the next, I don't know, a year or two, searching for specific, very specific nanomaterials in a general search engine like Google search will start to work, which is I think very exciting. Now, I mentioned the ontology for classification. We can also use this for very specific materials. Um, um, and we've been doing that for the JRC materials, and yesterday I shared a link to that. For those who haven't seen that link yet, please ping me in the chat, and I will copy paste it again. But we can also do that for annotating other things. So the OECD defines a number of nanomaterials, and this particular data set was of interest because of the naked database. The naked database is around exposure. And in the workgroup F, or the workgroup 4 at the time, we worked on annotating the content of that database, and they were using the OECD nanomaterials. So to enable the semantic annotation, we linked those OECD nanomaterials at the time with ontology terms. And that specification you will find online on the link given there. If you go to specs.inanimapper.org, you should still be able to find it. Oh yeah, well, this is the page that I showed yesterday. I showed it yesterday, particularly because of the annotation of research articles with identifiers from this ontology, allowing you to easily track the literature about one of the specific JOC representative industrial materials. And if you haven't noticed that yesterday, for each of these materials, you have a Scholia page, and that Scholia page actually has an RSS feed, a news feed. So if you use something like Feedly, you can actually get alerted if there is new research out on any of the JRC materials, which is slowly picking up, but not a lot. This is also the context, of course, of using identifiers in general for specific materials, like with the European Registry of Materials. That one is not so much an ontology, but still a global a provider of global unique identifiers, just like ontologies are doing that for concepts. I'll skip this one for now. That is the bioschemas annotation. If people are interested, if they have data sets or chemical substances on web pages, and you want to learn on how to do that, the Elixir toxicology community can help with that. We've been doing this kind of thing, and we're very eager to help that, and that will ensure that that we can provide this information also into this global search engine being developed in the UK. More JSON markup. So I think I'm doing really well on time. If this is the acknowledgement slide, there is a lot more to say about ontologies, and this is exactly what the hands-on material will do in a second. But before we go there, I just want to make sure that that I acknowledge everyone. And this slide is not giving full credit to everything, but for the ontology, some key things are the NanoCommons project, in particular Jenna Hastings, who worked at the European Bioinformatics Institute at the time. The projects that have been maintaining the ontology, so NanoSolve actually should be adding here, but I also absolutely want to extend it to the full nano safety cluster and the United States Nano Working Group, all partners that have been collaborating on this on this shared vocabulary, shared terms. In the bottom right here, actually, you see the EU one, the EU Observatory of Nanomaterials, which is part of that is using actually the NanoMapper database software. So also there you can find the use of the ontology return. Right. So not entirely. So which slide am I actually? Quickly checking. A few more. Okay. This last one actually is quite interesting because this takes us back to the Sparkle querying of loading of yesterday. So here we have the hierarchy of the ontologies and the genotoxicity and metal oxides. So if we translate this, if we want to answer the question, for example, which metal oxides show a form of genotoxicity, we can literally formulate it in that way. We can create a Sparkle query that queries a database with nanosafety data and just say, well, give me all metal oxides, because there is an ontology term for that from the nanoparticle ontology, and for the assays from the bioassay ontology. And the hierarchy of that will ensure that it picks up the right information, and then you get a result like in this table. And you can see here that we indeed have different, two kinds of metal oxide, two kinds of titanium oxide and a zinc oxide. It's just the first 10, what is it, nine rows of this table. And we see a specific genotoxicity assay here based on the Comet assay. And so the Sparkle query actually looks like this. So this is a query that we developed at the time at the end of the NanoMapper project. This table about the metal oxides and genotoxicity, I don't have the Sparkle query. This Sparkle query looks like this, actually. It's just replacing a couple of ontology terms. Here we have the Sparkle query that almost does the same thing, but asks actually for size information. And if you've been dealing with physical chemical characterization of nanomaterials, you see quite a different representations of the size of the material. But thanks to ontologies, we can actually group over that by using the subclassing. The subclassing is with the RDF schema ontology subclass of. That is how web ontology language ontologies represent the hierarchy of that ontology. Down here we still see the bioassay bit, and the pattern refers to the size. In this case, you can, for example, also use this for data completeness. So that's what this slide is about. Now I have a couple of slides, but I will skip that. So I said something about the upstream ontologies that we're reusing, but they come with new releases all the time, and we automated that by using automatic building, a continuous integration system called Jenkins, where we update the newer versions of upstream ontologies. We extract the bits that we want. We have a configuration of that. We know exactly what we want and pull that into the new releases of the NanoMapper ontology. And for that, we use Slimmer and more recently a robot, the latter thanks to the work from Laurent, to extract those informations. And that feeds a bit into the last bit of the experimental part about the extensions of ontologies. So some extensions are a lot easier than others. If we reuse something from another ontology, we just have to say, okay, give me that part of the ontology, that subtree of the ontology. Okay, now I'm really at the end of this of the introduction presentation. I hope this gives you some idea of how the ontologies link to the semantic web part, and I hope that this gives you a good foundation to work on the practical part.